back to the deep dive. Your shortcut to being well-informed, digging into the source material to pull out the absolute best nuggets of knowledge for you. Today, we are plunging into a really fascinating corner of quantum technology. Our topic for this deep dive is how we can take incredibly faint quantum signals, specifically at microwave frequencies, and amplify them using special superconducting circuits, Josephson circuits. It's basically about boosting the whisper of a single photon without messing up its quantum message.
And the source guiding our journey today is, a really insightful review paper. It's titled Introduction to Parametric Amplification of Quantum Signals with Josephson Circuits by Ananda Roy and Michel Devereux. It really lays out both the fundamental physics and the clever ways these amplifiers are actually built.
So our mission in this deep dive is to walk through the core ideas presented in this paper. We want to unpack what's happening physically, why it matters for things like quantum computing.
Yeah, and other technologies too.
And how these circuits pull it off. We'll loosely follow the paper's structure, and we'll even point you to a few key figures and equation sets along the way, just in case you want to follow along with the paper yourself or maybe dive deeper later.
Exactly. And it's important to understand why this is such a challenging and, crucial problem. Microwave photons are essential for many quantum information systems, but their energy is tiny, just minuscule compared to, say, visible light photons.
Right.
So trying to detect or manipulate them requires amplifiers that add the absolute minimum amount of noise possible. The theoretical minimum is set by quantum mechanics itself, what's known as the standard quantum limit. This deep dive explores how Josephson circuits are engineered to get incredibly close to that limit.
Okay, let's unpack this, starting with the context the paper sets in its introduction. They highlight the energy scale. Microwave photons, typically what, 3 to 12 gigahertz?
That's the range, yeah.
They have about 100,000 times less energy than visible light photons.
Yeah.
That's huge.
It is. And yet, they emphasize at the extremely low temperatures needed for quantum circuits, down around 20 millikelvin,
Colder than outer space.
Right. Colder than outer space, you absolutely can work with signals equivalent to single microwave photons. It requires special techniques, definitely, but it's possible.
So what are the big advantages, then, of working with these microwave quantum signals using superconducting circuits? What does the paper point out?
Well, they mention several things. You get excellent control over the shape and path of the signal envelopes and spatial modes. Microwave components and sources can be very stable when cooled down that low. Plus, the circuits can often be built using lumped elements on a chip, which makes designing and controlling spatial modes much easier than, say, in optics.
And this is where the star component of the paper comes in, the Josephson tunnel junction.
Yeah.
What makes this simple-looking device so critical for this advanced amplification?
It's really all about its nonlinearity. Unlike a regular resistor or capacitor, a Josephson junction's electrical properties depend nonlinearly on the quantum state. And this holds even down to the single photon level. This nonlinearity is the key.
And it's practical, too.
Yeah, it's also simple to fabricate, pretty robust, and when superconducting, ideally non-dissipative, basically no energy loss.
Okay. The paper explains that this unique nonlinearity lets you do all sorts of quantum signal processing, both digital and analog. But for this review, they focus tightly on one area: analog Josephson amplifiers that are pumped with microwave tones.
Precisely. They focus on devices that use strong classical microwave drives. These are the pumps to achieve linear amplification of weak quantum signals. And the goal is operating right near that lowest possible noise level, the standard quantum limit.
Got it. And the paper maps out its discussion, which serves as our map too. We'll explore what these quantum signals actually mean in this context, the key mathematical tool to describe circuits interacting with them. That's the quantum Langevin equation.
Right, the QLE.
The theoretical models of how amplification works, the actual circuit implementations, and finally, the outlook. So let's start by tackling that fundamental question. What is a quantum electromagnetic signal propagating along a transmission line? That's the focus of the paper's Section 2.
Right. Section 2 dives deep into this. Think about a simple transmission line, like a coaxial cable. Figure 1 in the paper shows this conceptually. Classically, you describe waves traveling left or right using voltage and current. To go quantum, they introduce wave amplitude operators for these propagating waves.
Which immediately sounds complicated. They talk about how the standard quantum description you might use for, like, a photon stuck in a box doesn't directly apply here.
Yeah.
Something about tricky commutation relations for operators defined in the time domain. I think that's EQ 6, 7, and then 12 through 16 maybe.
Yeah, it is tricky. The time domain operators don't behave quite like the nice, simple ladder operators we're used to. So a key step is moving to the frequency domain. They define frequency-dependent ladder operators, that's EQ 8 and 9, using Fourier transforms. These frequency operators do have commutation relations, like in EQ 10 and 11, that look much more familiar. They look like the ones we use for standing waves or simple harmonic oscillators, like the relation shown later in EQ 29.
Okay, so frequency space makes the operators look, well, nicer. But how do you get back to the idea of a discrete photon actually traveling along the line?
That's where the paper introduces the concept of using an orthonormal basis of wavelets. That's EQ 17 through 19. Think of these as fundamental time-limited packets of energy. They need careful definitions regarding positive and negative frequency parts, like in EQ 20 and 21. By defining operators based on these wavelets, you can properly second quantize the field. That's EQ 26 and 27. These new wavelet-based operators do satisfy the standard bosonic commutation relations needed to define discrete quanta.
Ah, okay. So a photon, in this context, isn't just a point particle bouncing around. It's an elementary excitation described by one of these spatiotemporal wavelets, corresponding to a field state that's, distinct from the vacuum state, like in EQ 30 and 31.
Exactly. The state of the signal can then be described as a superposition of these single photon excitations. Or you could have multiphoton states within these wavelets. Those are the Fock states, EQ 32, 33. And you can have excitations across different modes, EQ 34. This leads to the quantum state being described by, well, exponentially many coefficients compared to a classical signal. As hinted in EQ 35, it really highlights the richness of the quantum description. Entanglement shows up here, too.
And they briefly mention coherent states, EQ 36 through 39, as a special case.
Yes, these behave most like classical signals. They're useful because they have this property of remaining coherent regardless of how you chop up the signal into different wavelet bases. Yeah, and they touch on the density matrix, like in EQ 40 and 41, for describing non-pure or mixed states, and how information is quantified quantum mechanically using entropy, like in EQ 42 and 43. The big takeaway from this section is really establishing a rigorous mathematical framework for describing these quantum of energy as they travel along a wire, ready to interact with the circuit.
Okay, that gives us a handle on what the signals are, mathematically at least. Now, how do we model what happens when one of these quantum signals hits a circuit? How does the circuit interact with the line and its inherent quantum noise? That brings us to the paper's section 3 and the quantum Langevin equation.
This is the key tool. The general setup is a circuit connected to transmission lines, like the schematic you see in Figure 2a. The quantum Langevin equation, or QLE, provides a way to describe the quantum dynamics of the circuit elements while they're coupled to these external electromagnetic fields.
We introduce the simplest case first, a single circuit mode coupled to a single transmission line, often represented as needing a circulator to separate input and output, like in Figure 2b.
That's right. That setup models things like reflection amplifiers or directional amplifiers, too. And they present the core QLE in EQ 44. Let's maybe break down the physics captured by the terms on the right side. It's really important.
Okay.
First, you have the term involving the commutator, HA. This is just standard quantum mechanical evolution of the circuit's internal degrees of freedom governed by its Hamiltonian H. This is where the circuit's nonlinearity, if it has one, comes into play.
Right, the internal dynamics.
Second, there's a damping term, Me2A. This represents energy leaking out of the circuit mode into the transmission line. It's dissipation. And it relies on assumptions like the Markov approximation, basically, that the line acts like a simple, frequency-independent, ohmic environment.
Memoryless, sort of.
Yeah, memoryless. And that the coupling is weak compared to the circuit's dynamics. That's the rotating wave approximation, or RWA. So P should be much smaller than the transition frequencies.
Okay, internal dynamics damping was a third term.
Third, you have the term SHIRP. This is the input field from the transmission line driving the circuit. It includes the incoming signal you care about, but critically, it must also include the vacuum fluctuations, the quantum noise of the transmission line itself.
And that square root of kappa factor, Chuck, tying the damping term and the input drive term together.
Yeah.
That seems significant, right?
Absolutely. It's a direct manifestation of the fluctuation dissipation theorem in the quantum realm. The rate at which the circuit loses energy, CHIP, is fundamentally linked to the strength of the random driving force from the environment, which here is the quantum fluctuations of the vacuum.
And the paper makes the crucial point, I think it's around EQ 46, that at typical operating temperatures like 20 milliK and these microwave frequencies,
Mm,
quantum fluctuations completely swamp any thermal noise effects. You're dealing purely with quantum noise from the vacuum.
that's exactly right. Thermal noise is negligible. Then, connecting the internal circuit dynamics to the external world, they provide the input-output equation. That's EQ47. This equation relates the quantum amplitude of the circuit mode, A, to the incoming and outgoing wave amplitudes on the transmission line, in and out. And again, it features that seek factor.
Use the simple example of just a linear harmonic oscillator circuit coupled to a line, shown in Figure 3, to show how solving these equations gives familiar results, like the reflection coefficient, which you can see in EQ 48 through 50, in the frequency domain.
Yes, and they show that while the RWA gives a simplified picture with a single pole, EQ50, a more exact treatment, still assuming Markov but without RWA, gives a pair of poles, EQ51. This demonstrates that the RWA is an excellent approximation in the regime where these amplifiers usually operate near resonance and with weak damping. It simplifies things nicely.
And this whole framework scales up, doesn't it? They show how the QLE and input-output equations can be generalized to circuits with multiple modes and multiple ports, like in Figure 4, and the generalized equations are EQ 52 and 53.
Exactly. The QLE provides the complete quantum picture. It models how the circuit's internal state evolves under its own Hamiltonian, how it loses energy to the lines, and how it's driven by the quantum fields coming in from those lines, including the unavoidable vacuum noise.
Okay, so we know what the quantum signals are conceptually, more or less. And we have the mathematical tool, the QLE, to describe how circuits interact with them and their inherent noise. Now, the big question: how do we use this to get amplification? That's what Section 4 model amplifiers tackles.
Right. The core idea here, the central concept really, is that amplification emerges from driving a nonlinear circuit element in such a way that its behavior can be described by an effective, time-dependent quadratic Hamiltonian. CEQ 54. This might sound a bit abstract, but think of it as effectively creating time-varying coupling strengths or frequency shifts between different signal modes. And this is all powered by strong, classical pump tones.
So the pump injects energy into the circuit, and the circuit's nonlinearity kind of mixes the pump energy with the weak input signal energy to boost the signal. Is that the gist?
Precisely. The quadratic terms in that effective Hamiltonian EQ 54 represent these interactions, driven at frequencies related to the pump. The paper focuses on two fundamental ways this can happen, leading to two main types of parametric amplifiers.
Okay, what are they?
First, there's the non-degenerate parametric amplifier, or NDPA. This involves interaction between two distinct signal modes. Let's call them Mode A and Mode B. Often they're at different frequencies, a signal frequency, OS, and an idler frequency. Its core effective Hamiltonian is shown in EQ55. The pump frequency, which they call AB, is typically near the sum of the signal and idler frequencies. So OS plus OI is approximately equal to AB. Figure 5a illustrates this frequency relationship nicely. The circuit usually has two ports mentioned via the couplings cob in EQ55, one primarily for the signal mode and one for the idler.
Okay, two modes, signal and idler. What's the second type?
Second, the degenerate parametric amplifier, or DPA. This one's simpler. It involves only a single signal mode. Its Hamiltonian is in EQ56. The signal and idler are essentially at the same frequency relative to the mode resonance. This requires the pump frequency to be near twice the mode resonant frequency, so I is about 2. Figure 5b shows this frequency picture. This device typically has just a single port where the signal, idler, and pump all interact. EQ56 mentions only one coupling, A.
Okay, so NDPA for two distinct modes or frequencies, and DPA for one mode where signal and idler are effectively at the same frequency relative to the mode. How do we analyze their amplification properties then?
Well, using the QLE and input-output framework from Section 3, you can derive scattering relations. These describe how incoming waves at various frequencies are converted or reflected into outgoing waves. For the NDPA, this leads to a scattering matrix, shown as EQ of 57.
Why is that matrix 4 by 4? That seems big.
Because it's describing incoming and outgoing waves at two different frequencies, usually taken as plus O and F relative to resonance for each of the two modes involved, mode A and mode B. So 2 frequencies by 2 modes equals 4 channels. The elements of this matrix, given in EQ 58 through 61, depend on properties of the individual modes, like their susceptibility in EQ 62. And crucially, they depend on the strength of the pump-driven interaction between the modes, which is captured by the parameter OB in EQs of 63, sometimes called mode cooperativity squared. They show that under optimal tuning conditions, the scattering matrix simplifies quite a bit, like in EQ64, and you can derive the power gain for the signal that's G0 in EQ65. And a key condition for stable amplification is that this interaction strength parameter, HAB, must be less than 1. If it hits 1 or goes above, the amplifier breaks into spontaneous oscillation. Not good.
Right. You want amplification, not an oscillator. Got it. What about the DPA scattering matrix?
The DPA scattering matrix EQ66 is also 4x4, representing the two frequency sidebands on the single port, but all the action happens on that one port. When the pump is tuned exactly to twice the mode frequency, AAU2OA, the equations simplify significantly, as shown before EQ67. Here, it becomes more natural to talk about the signal in terms of its in-phase and quadrature components. They define these in EQ68.
Like amplitude and phase modulation components.
Exactly. EQ69 and 70 show that connection. These components essentially describe the signal's amplitude variations along two orthogonal axes in phase space.
And in this in-phase quadrature basis, the scattering matrix becomes diagonal. That's EQ 71 and 72.
Yes, which is really neat because it immediately reveals the DPA's unique property shown in EQ 73. The product of the gains for the two quadratures is exactly 1, so G parallel times G perpendicular equals 1. This means if one quadrature is amplified, so its gain is greater than 1, the other quadrature must be de-amplified. Its gain has to be less than 1.
This is where squeezing comes in, right? You mentioned that.
Exactly. If you feed just vacuum noise into a DPA, the output fluctuations will be squeezed. They'll be reduced below the vacuum level in one quadrature, but at the expense of increased fluctuations in the other, orthogonal quadrature. The NDPA, by the way, can produce something called two-mode squeezing between the signal and idler outputs.
Interesting.
The paper then explains how an NDPA is often used as a kind of RF operational amplifier, essentially. You typically connect the idler port to a cold termination, just a 50-ohm load at low temperature. Then the output signal coming back from the signal port, described in EQ74, shows the amplified input signal, but also a second term. Yes, noise originating from the idler port's termination, which gets converted and amplified. This unavoidable added noise, when referred back to the amplifier's input, amounts to typically half a photon's worth of noise at zero temperature, especially in the limit of large gain.
And you mentioned earlier why this noise has to be added. It's not just bad engineering.
No, it's fundamental physics. This added noise ensures that the output operators still satisfy the correct quantum commutation relations, like EQ75. It's a direct consequence of the Heisenberg uncertainty principle. Amplifying a signal is like trying to measure its non-commuting properties, its quadratures, simultaneously and with arbitrary precision. You can't. The added quantum noise is the absolute minimum required by quantum mechanics. An amplifier that adds only this irreducible noise is called quantum limited. That's the goal.
Okay, so that's the theoretical foundation. Effective quadratic Hamiltonians. DPA amplifies one quadrature while de-amplifying the other, squeezing noise. And DPA amplifies signal and idler while adding unavoidable idler noise. And both, ideally, only add the minimum quantum noise set by physics itself. Now, how do we actually build these things using Josephson circuits? That takes us to Section 5.
Right. Section 5 dives into practical circuit implementations. They start with Section 5.1, looking at a parametrically driven oscillator using a single Josephson element, sometimes called a SNAL, or based on Duffing-like dynamics. Figure 6 shows a concept.
This relies on the nonlinearity inherent in the single Josephson junctions energy phase relationship, right?
Yeah.
The cosine potential.
Yes, exactly. The circuit's Hamiltonian, EQ 76 and 77, has terms for its capacitance and the nonlinear Josephson inductance, which comes from that cosine. By assuming small phase excursions around the minimum and expanding the cosine term, keeping up to the fourth order, the O term, you get an effective Hamiltonian. That's EQ 79 after applying the RWA. It includes a resonant frequency, cosa, and a Kerr nonlinearity, the K term. The Kerr term basically makes the resonant frequency depend on the number of photons already in the mode.
So the frequency shifts with energy.
Precisely. The QLE for the system, EQ80, shows these internal Kerr dynamics, the damping R, and the input drive. To get amplification, you apply a strong classical pump tone at frequency in addition to the signal. By treating the pump as a large classical amplitude, which you can solve for using EQ84 and 85, the system behaves like an effective DPA.
And this leads back to the effective DPA Hamiltonian we saw in Section 4, right? That's EQ 87.
Exactly, with the effective frequency and coupling terms defined in EQ 88 and 89, and the required pump frequency in EQ 90. Notice the pump frequency is near the mode resonance frequency cus here.
But they mention drawbacks.
Yeah, a key drawback of this type is that the amplifier center frequency actually shifts depending on the pump power because FUSA depends on EQ88. That can be inconvenient. Also, the strong pump and the weak signal share the same port, which means you need really good filters to separate them.
Makes sense. What's the next implementation they discuss?
Section 5.2 introduces a DPA based on a DC squed. That's shown in Figure 7. Remember, a DC squed is a loop with two Josephson junctions in parallel. Here, the trick isn't the inherent Kerr nonlinearity so much, but rather modulating the magnetic flux threading the squed loop at the pump frequency.
How does modulating the flux lead to parametric amplification?
Well, the effective inductance of the DC squed depends nonlinearly on the magnetic flux bias. That's EQ91. So by modulating the external flux around a specific bias point, as in EQ92, with an RF tone, often via a nearby current line, see Figure 7, you parametrically modulate the squed-wide's inductance. This, in turn, modulates the resonant frequency of the circuit it's part of. Classically, this is like having a swing whose rope length changes periodically, or a spring whose stiffness changes over time. EQ93 shows the classical equation.
So it's linear, but time-varying.
Exactly. Quantum mechanically, in the weak damping limit, this flux modulation directly realizes the DPA Hamiltonian EQ94. But crucially, look at the pump frequency required, EQ95 and 96. It needs to be near twice the resonant frequency of the mode, E2 NOA, not just near O itself, unlike the Duffenkerr case.
And that's a key advantage they note, right? Since the pump is at roughly twice the frequency of the signal in idler, which are both near Ura, it's much easier to separate the intense pump tone from the weak signal using frequency filters.
Right. This makes coupling the pump in and filtering it out much more manageable in practice.
Okay, so those are two ways to build a DPA. How about the NDPA, the non-degenerate one?
Section 5.3 presents an implementation of the NDPA using a really clever circuit called the Josephson ring modulator, or JRM. That's in Figure 8. This consists of 4 Josephson junctions arranged in a ring, and it's designed specifically to couple 3 different microwave resonant modes. They call it a purely dispersive 3-wave mixer.
3-wave mixing.
Yeah. The Hamiltonian for this circuit, EQ97, includes a special trilinear coupling term involving operators from all 3 modes. Let's call them A, B, and C.
Yeah.
This G3 term is key. The idea is to drive one of these modes, say mode C, with a strong classical pump tone. Because the pump field is so much stronger than the quantum signals in modes A and B, mode C's operator effectively just becomes a classical oscillating number proportional to the pump amplitude acts.
And when you do that substitution, what does the Hamiltonian look like for modes A and B?
It simplifies to an effective Hamiltonian, EQ99, that describes an interaction between modes A and B, and this interaction is modulated at the pump frequency applied to mode C. The coupling strength is given in EQ100, and the effective pump frequency in EQ101.
So it looks like the pump on C is mediating an interaction between A and B.
Precisely. And then within the rotating wave approximation, if the pump frequency AB is tuned near the sum of the frequencies of modes A and B, ABO plus sub, you neglect the fast-rotating terms, and you recover the generic NDPA Hamiltonian EQ1 or 2 that we discussed back in Section 4.
So this circuit directly implements that 2-mode non-degenerate interaction needed for the NDPA. They also mention a nice property, that this trilinear coupling, unlike the Kerr term, doesn't shift the mode frequencies themselves at the lowest order when driven, helps with stability.
Exactly. This ring modulator configuration provides a really elegant way to achieve that desired non-degenerate parametric interaction by driving a specific separate mode as the pump.
Wow, okay. That's quite a detailed tour through the theory and these different, quite clever circuit designs. So, wrapping up with Section 6, the conclusions and perspectives, what's the main takeaway they want us to remember from all this?
Well, the core message, I think, is that parametric amplification in Josephson circuits fundamentally boils down to creating an effective, time-dependent quadratic Hamiltonian. This is done by using strong classical pump tones to drive the circuit's inherent nonlinearity. And the 2 main flavors are the degenerate, DPA, and non-degenerate, NDPA, corresponding to different forms of this effective Hamiltonian.
And Figure 9 is a great visual summary they provide. It classifies these different amplifier types based on things like, well, whether they use the degenerate or non-degenerate process, how many modes are involved in the core interaction, what kind of mixing process is dominant. They explain that a 3-wave process can sometimes involve a DC current from flux biasing acting like one of the waves.
Right, replacing an RF pump with a DC bias effectively.
And also how many ports the signal and pump use, whether everything's on one port or separated.
Yes, and you can generally see how circuits tend to increase in complexity as you move from the upper left of that figure, often simpler, one-port DPA implementations towards the lower right, which includes more complex, potentially multi-port NDPA designs aiming for cleaner signal pump separation and maybe other features.
They also briefly mention topics they didn't really cover in this review, but are important research areas like an amplifier's dynamic range, how strong a signal it can handle before saturating.
Yeah, that's critical. Also, directionality, making the amplifier work only one way overall efficiency, and using these devices for frequency conversion, not just amplification.
All active areas.
Absolutely. These are all areas of active research and development. And looking ahead, they touch on ongoing challenges like improving the gain bandwidth product. You usually want high gain over a wide frequency range, but there are trade-offs.
The gain bandwidth limit.
Exactly. And also better understanding how to operate stably right near that instability threshold where the gain is highest without the amplifier just spontaneously oscillating.
Tricky balancing act.
It is. So thinking about this entire deep dive, the subtle definition of a propagating quantum photon, the detailed modeling with the QLE, the fundamental requirements for minimal added noise from quantum mechanics itself, and then these ingenious circuit designs using Josephson junctions, these tiny superconducting elements all operating at these extreme cryogenic temperatures. It really highlights the incredible level of physics and engineering required just to interact with and amplify these incredibly faint quantum signals. We're talking single photons here.
It really does, and it makes you wonder, as quantum systems inevitably get larger and more complex, maybe relying on thousands or even millions of these delicate components someday, how do researchers and engineers balance this intricate, precise control needed at the quantum level with the demands of building robust, scalable technologies? It feels like a huge challenge for the future of quantum computing and communication. What do you think?
I think that's exactly the right question to be asking. Balancing the exquisite sensitivity and quantum coherence needed with the practicalities of scaling up. That's really where a lot of the hard work lies ahead. How do you maintain this performance across large, integrated systems? It's a major frontier.
Well, with that thought to ponder, we've journeyed through the Roy and Devroy paper, exploring the fascinating world of parametric amplification of quantum signals using Josephson circuits. We went from the fundamental definition of the traveling photon to the theory of quantum-limited amplification and the practical circuits that make it happen. Thank you so much for joining us on this deep dive.
Yeah, thanks for listening. We hope this discussion maybe encourages you to explore the source paper further or perhaps dig into some related topics in this really exciting field.
We'll see you on the next one.